Hey, welcome to The Explainer. Today, we're diving into a piece of tech that is literally all around you, but you've probably never even seen it. It's called the VR sensor. That stands for Variable Reluctance, and it's the secret sauce for how so many machines understand movement. I mean, really think about it. You've probably been there, right? You have to slam on the brakes on a slippery, wet road, and the car just grips and stops safely. How in the world does it know exactly how fast each wheel is spinning to keep you from skidding? Well, it's not magic. It's some really, really clever physics. Because tucked away deep inside your car's wheel assembly, there's this little unassuming sensor. Its one and only job is to constantly watch that wheel, feeding vital information to systems like your anti-lock brakes. And the way it works is just brilliantly simple. So to really get how this sensor works, we gotta talk about the core idea it's built on, variable reluctance. I know, that might sound a little technical, but trust me, the idea behind it is actually super straightforward. This is the perfect way to think about it. You already know about electrical resistance, right? It's what pushes back against the flow of electricity in a wire. Well, reluctance does the exact same thing, but for magnetic fields. It's just a measure of how hard it is for a magnetic field to pass through a material. And this image just nails the concept. Look over on the left. The magnet is trying to push its field across that big air gap. Air is just terrible at conducting magnetic fields, so it has high reluctance. It's a really tough path. But now, look at the right. We slide a metal bar in there, making the air gap tiny. Suddenly, the magnetic field has this easy superhighway to travel through the iron, which has very low reluctance. See how the field gets all focused and concentrated? That's the whole idea. And that is the key. When the path for the magnetic field changes, the reluctance changes right along with it. And that continuous change is what we call variable reluctance. It's this simple principle, this changing opposition to a magnetic field, that the entire sensor is designed to detect. All right, so we've got the physics down. Now let's crack one of these things open, metaphorically speaking, and see what actually makes it tick. So this is what one looks like out in the wild. You can see it's built like a little tank. That threaded metal body means you can screw it in super securely and get the positioning just right. And it has to be tough, because these things live in really harsh places. Think hot engines or grimy wheel wells, getting vibrated and shaken all day long. Now, this diagram is like giving us X-ray vision. And when you look inside, it's shockingly simple, isn't it? There's no complex electronics, no little moving parts inside the sensor itself. It's literally just three core components working together with a target. In this case, that gear wheel. So let's break that down. First up, you've got a permanent magnet. Its job is easy. Just create a constant magnetic field. Second, there's a soft iron core. You can think of this like a lens, but for magnetism. It grabs that field, focuses it, and shoots it out of the tip of the sensor. And finally, wrapped all around that core is a coil of wire. And this is where the magic happens. This is what's actually going to generate our signal. So we have the components and we understand the physics. The big question is, how do they all team up to turn the physical motion of a spinning gear into a useful electrical signal that a computer can actually understand? The entire operation is kind of like a little three-step dance that just repeats over and over again every single time a gear tooth passes by the sensor. Let's walk through it. Step 1. A gear tooth approaches the sensor. Now remember that iron bar from earlier? The tooth acts just like it. It shrinks the air gap, creating an easy, low-reluctance path for the magnetic field. This makes the magnetic flux, the concentration of the field, increase really quickly. And that change induces a positive voltage in our wire coil. Step 2. The tooth is perfectly aligned with the sensor's core. At this exact moment, the magnetic flux is at its absolute peak. But here's the trick. For just a split second, it's not changing. And since the voltage only gets created by a change in flux, the voltage drops to zero. This is called the zero crossing, and it's an incredibly important and precise timing reference. And finally, step 3. The tooth moves away. The air gap opens back up, reluctance goes way up, and the magnetic field collapses back to where it started. This rapid decrease in flux induces a voltage in the opposite direction, a negative voltage. You put all 3 steps together, and for every passing tooth, you get this beautiful, clean, wave-like signal. So we've gone from the physics to the internal workings and a signal it creates. Let's bring this all back to where we started, the real world. And here it is. This whole wheel hub assembly has this technology built right in. That VR sensor is pointed at a toothed ring on the inside. As the wheel spins, the sensor is just counting the teeth as they fly by, generating that wave signal.
The faster the wave, the faster the wheel is spinning. That signal goes right to the car's computer, enabling things like anti-lock braking and traction control.
It's just such an incredibly elegant system. By using nothing more than a magnet, a piece of iron, and a coil of wire, it translates physical motion directly into critical data. And get this, because it generates its own voltage, it doesn't even need a power source. It's just a perfect example of simple physics leading to powerful, life-saving results.
It really makes you think, doesn't it? This one sensor is a key part of modern safety, but it operates completely out of sight. So it makes you wonder, what other invisible sensors are quietly working all around us right now, making our modern world possible?